Dear students, let us continue our video lectures. Let me share the screen. In this video lecture, let us discuss what is the uncertainty involved in analyzing time and frequency content of a given signal. In the previous video lecture, we have seen a definition of short time Fourier transform. We have also seen by varying the window function in the short time Fourier transform, we can effectively localize in time. And we will see more discussion on it now in this video lecture. This video lecture also serves as an important guidelines to design better time frequency transformations. As discussed in the previous video lecture, usually we are interested not just knowing the frequencies of a given signal, and in general we are interested in at what time durations those frequency has occurred. Similarly, if particular frequency is given, a particular time duration is given, we want to know what are all the frequencies at that given time duration. So in essence, if we have a if we give a window in the time, and if we have a set of frequency in the frequency domain, we would essentially like to localize what are all the frequency content that is there in this window has occurred at what time duration. So essentially we would like to localize the frequency content both in time and frequency. The information of the signal both in time and frequency. Assume that we have a signal x of t, and we find Fourier transform of it through inner product of x of t with e power j omega t. So we are multiplying with a particular complex exponential. So we are analyzing a particular set of frequencies. So we can easily confine on which of the frequency we are analyzing. However, we are taking here the all time duration to analyze this. For understanding the region in time frequency plot, this can be referred to as time frequency plot. So this is in fact time frequency, but please note that this is a two-dimensional plot. It can be a mesh plot or a surface plot. So where the magnitude of time frequency quotients will be there in the third axis. That are coming out. Fine. So essentially what we are plotting here is in some sense x of j omega comma tau of this order. This is what we are plotting. So let me write this here. This is what we are trying to do with different time, and this is at different frequency. Since we we have denoted f as a running variable, let us denote for frequency as well a temporary variable x of r comma tau. R is a temporary variable for frequency, okay, and tau is a temporary variable for time, okay, temporary variable for time, okay, and R is temporary variable for frequency. Fine. So with this setting, let us start and try to analyze. Okay, for a like what is the how precisely local can we localize a information in this time frequency plot of a given signal x of t. Okay, so once we find x of j omega and x of t, we have with us the signal and its frequency content. Given this, what time frequency like analysis theory says is you cannot localize the time and frequency information of a signal completely. What it indicates is if you have a signal like this, okay, so if I consider only a particular instance of time, okay, any particular instance of time, there is no meaning of the frequency content at a given instant of time t. However, the frequency is the variation in time, and hence if I take only a duration, then frequency makes sense. Okay, frequency by definition is variation of signal in time. Okay, and hence makes sense only in a given duration, not at a given instant. Fine. At the same time, that this implies that you cannot localize the frequency content perfectly in time. Okay, you cannot tell a time equal to t naught. You can only localize over a window of time. Okay, so frequency information okay can only be localized over a window, okay, or duration of time. The question here is how small this window can be. Okay, that is localizing in time. Okay, delta t or delta tau. So how small this window can be. Minimum delta t is how much? Okay, that is the question. Okay, this is the problem of localizing the frequency content, okay, in time. Fine. As you know, the frequency means, please note that the frequency by definition is variation of signal in time. Okay, by definition, frequency is this. Okay. The next question is, see, if I say these are all the frequencies present, okay, in a given signal. So what? So omega naught maybe they're here. Okay, so maybe they're here, etc. So can I localize precisely that these are all the frequencies present, okay, in the given signal? Okay, so that is the next question. So can I tell that this is the only frequency present? Okay. Particularly, can we say that frequency omega naught alone is present or not? Okay, so that is localizing in frequency. Okay, so let us see now what time frequency uncertainty analysis says is the mean value, okay, in time for the uncertainty of this information, time information, is given by t into x of t whole square dt. Okay, by this is in some sense statistically defined mean value of the signal amplitude x of t, as you can see here from the definition, right? But this mean value of the signal, okay, is defined for entire duration. Please note here, we are not defining over a window. Okay, we are defining for entire duration here in this definition. Later, when we define different time frequency analysis things, we can also see over a window. For example, for short time Fourier transform, when I consider only this duration of window, okay, for my analysis, okay, then I can consider this to be defined only from this duration, in this duration. Okay, mu t is defined only in this duration. Okay, then the value of mu t also will be somewhere in this, okay, only along this axis. That means only along this uh, mm, this region. Okay, it will not be anywhere. However, this is now whatever we have defined is extending from minus infinity to infinity in time. Okay, this mu t can be anywhere in time. Please note that. Okay, so but later when we define for short time Fourier transform, it may range only in this. Okay, so let this be mu t. But the signal magnitude also may have a variance in time. So sigma square t, that is defined in time. Let us write with slightly different color to have a better contrast. Sigma square t. How do we define this? In magnitude t minus mu t whole square into x of t whole square dt by integral x of t whole square dt. Again, the definition of this integral also is calculated for minus infinity to infinity for Fourier transform. Whereas for short time Fourier transform, they may be calculated from over a window. Okay, please note that. So these two will give us an uncertainty window in time domain. That means, say in case essentially, if say if mu is here, okay, mu f is here, okay, and then sigma is up to here. Okay, so sigma defines, okay, roughly the uncertainty, like the spread over the mean value of the magnitudes of the signal. Okay, the mean value is given by this. So essentially, if we see this is the mean value, assume that of the signal. Okay, mean value is say some 2 or whatever, and this is the like spread of the signal. Okay, so this is given by mu f. Okay, and this is given by sigma f. Sorry, mu t and sigma t. Okay, that's what we are trying to say or conveying, that the uncertainty of the time window of the signal. Okay, so time window is mu t defined by mu t and sigma square t, where mu t gives the location of the time window and the sigma square t defines the duration of the time window. So the time window duration here, we can consider it as 2 times sigma t. Okay, okay, right. Now let us define the similar terms in the frequency domain, because when we write the Fourier transform through this, we have the frequency information with us. Okay, and hence from this we can define the mean value in the frequency domain is f for omega, okay, by fine. This gives which is the dominant frequency, okay, present in the frequency domain. Similarly, the spread is also can be written, that is sigma square f around this dominant frequency. This also may be defined for the whole region of frequencies if the like if we consider integral over whole region, otherwise over a window. Okay, so essentially see if for a given time frequency plot, okay, assume that we have got a value that is, say this is time and this is frequency, okay, and let this be, this value is given by mu t comma mu f. Fine, because this is given by mu t in time domain, okay, the mean of the time, and mu f is given by mean of frequency, okay, information. And then the uncertainty window is given by mu f and sigma f, and sigma t. So the uncertainty window may be, so for sigma f, it may be say up to here, assume that, and then for the sigma t may be up to here. Okay, that means sigma t is this, sigma f is this. So the width of the window, uncertainty window, if we consider, is essentially, okay, width of the uncertainty window, if we consider, is this. That means the information of the signal, even if when we take Fourier transform, is essentially has like centered around this mu f and mu t and mu f, and with a uncertainty of the information of this much. Okay, this is 2 times sigma t and then 2 times sigma f. Okay, so the area of this window is is 4 times sigma f into sigma t. If the signal magnitude and the frequency magnitudes are concentrated, okay, and they occur at, okay, at a given time, like at a close to a particular duration and frequency, then these values will be smaller. Otherwise, there is a quite uncertainty in understanding the information of the, like the localizing the time and frequency content of a signal. Okay, so the window, time frequency window, is defined by mu t, okay, plus or minus sigma t, to comma, okay, mu f plus or minus sigma f. Okay, please note that this has 4 coordinates. Fine. And what does like the uncertainty analysis for the time frequency information says is that you cannot localize the information both in time and frequency. That means if you take more duration, okay, in time, then you can precisely tell what is the frequency content, okay, of the signal in that duration. But if you take small duration, you are not very sure of the frequency content in this small duration. Okay, so there is a more uncertainty in frequency domain. If you localize more in time, there is a more uncertainty in the frequency domain. If you localize more in frequency, okay, that means if you don't localize more in time, you are certain about the frequency. So what it says is, so the time frequency localizations, okay, can be local either in time or in frequency, and the area of this uncertainty window, okay, is always, okay, greater than or equal to 2. Always greater than or equal to 2. This is by uncertainty principle. We will not go for the derivation here, but you can we will understand with few examples. That means you can only localize either in time or in frequency. Okay, that means what are all the possibilities if you have in time frequencies? You may have a window having very poor localization in time. Okay, that means here you can see, okay, poor localization in time. Okay, but better localization in frequency. For this, okay. You may also have other possibility wherein there may be like, okay, poor localization, better localization in time, and poor localization in frequency. Okay, so you can see that means, say you can tell the information of the signal. Okay, in this duration only has occurred these frequencies. Okay, so you're not sure which are all among these frequencies which have occurred. Okay, you are sure only that in this duration these frequencies have occurred. Okay, so there is a less confidence on the frequency content. You can't particularly say which frequency has occurred, okay, at what time. If you localize to this, you can tell only these frequencies. If you localize to this time, okay, if you are not very well localized in time, you may say that these are the frequencies present. Okay, so that is what is given by this uncertainty principle. Okay, so the window types that we have discussed, either rectangular or the Gaussian window, will tell us, okay, which is where we are localizing in time, what is happening in frequency. Just to analyze, let us start windowed Fourier transform with a rectangular window. Okay, let us first define windowed Fourier transform. How do we define? At short time Fourier transform, okay, as we have defined, inner product of x of t with a window function located at tau multiplied with complex exponential. Okay, so this window function for rectangular window function is 1 for t minus tau, okay, less than or equal to tau naught by 2. Okay, right? So let us see this. This is a rectangular window, right? Okay, so if we take a rectangular window that is more localized in time, okay, So this is 0 for example, and this is minus tau naught by 2 to tau naught by 2. That is, tau naught is small, imply more localized in time. That means in this duration only, I can say that, say at duration of tau, okay, this, if tau naught is very small, I can say that at this time, these frequencies are present. Okay, ideally, this tau naught, this is of impulse nature, very peak, like narrow window indicates that I am able to localize in time and say what are the frequencies present. Okay, it's Fourier transform if I take, see, we anyway, this windowed Fourier transform depends upon this window function. Okay, we are considering the signal Fourier transform only at this window function, and hence let us see what happens to the Fourier transform of the window function first. What will happen? Since it is more localized in time, okay, what if you take Fourier transform of this rectangular window, it will be a sinc function. Okay, but it's a wider sinc function. Okay, because this is roughly inversely proportional to, okay, this is in omega, okay, and hence this is in fact 2 pi by or tau naught or something like that. Okay, minus pi by tau naught. You can exactly try to find, but I minus 2 pi by tau naught to 2 pi by tau naught, something like this. So if this duration is tau naught, this will be 1 by in proportional to 1 by tau naught. Okay, this is a good localization in time, okay, and poor localization in frequency. That means what we are saying is the window function itself analyzes the shorter, like longer range of frequencies. I will not be able to tell which particular frequencies are present in that duration. Okay. Now let us take the window function that is of longer duration here in time, that is not very well localized in time. Then if you take the Fourier transform of this, you can see that this Fourier transform will be narrow. Okay, this is more like multiplying with this Fourier transform. Okay, because it's essentially multiplying here is convolution with this. So this essentially analyzes the frequency content, okay, in a narrow Fourier, like in a narrow window in the frequency domain. So rectangular window, if it is localized well in time, not that much effectively in frequency domain. Okay, so now let us consider a Gaussian window and see what its characteristics are. If we consider a narrow Gaussian here, let us consider purely narrow Gaussian. This is a narrow Gaussian here. Okay, so this is e power minus alpha. This alpha is small. Okay, effective in this case. And if you apply Fourier transform here, Fourier transform of Gaussian function is also a Gaussian. And this alpha now comes in the numerator, and hence this is a wider Gaussian. Please note that this axis is omega, and this axis is time. Okay, so same is the case here. Here also you can see that if it is narrower in the one domain, okay, in time domain, that means if it is not very well localized in time domain, then it will be more localized in the frequency domain. Okay, it is well localized in the frequency domain. So, however, for the Gaussian window, you can see that the localization ability is reasonably high, both in time and frequency domain, because we essentially capture the frequency information or that time information this around tau. That means if you have if we multiply with this window at tau, then we are giving more importance to samples exactly at tau and then tapered off Gaussian gradually. And this also has an effect in the frequency domain to have a window that has concentrated around a particular set of frequencies. However, for the short time Fourier transform, with any of the window functions, what it does is, okay, so it only localizes either in time, it localizes with a rectangular like window like this. Okay, that means it localizes with a fixed window width. See, if we usually, when we find out the short time Fourier transform, we fix the window at the beginning itself, and hence this window width is fixed. If this window width tau is fixed here, that determines the localization ability here. Okay, and similarly, this also fixes this. Okay, and hence it determines the localization ability in the frequency domain. So just to conclude this analysis, for a short time Fourier transform, if we see time frequency tiling, that means the uncertainties, say if we consider this is one window and this is another, and so on. So these are all the partitions in time. And so what we are doing is, instead of analyzing all times, we are analyzing at this time first. Okay. And then we are analyzing during this time first. All the frequency content we are trying to understand at this frequency next, at this frequency, at this frequency, okay, at this frequency, sorry, at this time, at this time. Okay, so what we are doing is, we are analyzing, we are trying to bring the windows in time and trying to get the frequency information in that window. Okay, that's what we are doing in short time Fourier transform. Okay, so essentially what will happen because of this mu, so for each of these windows, okay, we will have a mu t and sigma t square. Okay, and similarly we also have mu f and sigma f square. Okay, so you may, if mu t is this value for this, okay, and mu t mu f is this for this window, in this window, then this may be, say, let me write the time frequency tiles. Okay, this may be around this. Okay, similarly, so if this is the case, here I may have something like this. Okay, I may have here somewhere here. Okay, it may have something like this. This is based on the mu t and sigma t square, mu f and sigma f square in that time frequency, in that duration of time, what we get for the given signal. Okay, so these are all the, so essentially what we are doing is, we are analyzing the time frequency information is analyzed with fixed window. Fixed window duration, fixed duration window in time. Okay, for short time Fourier transform. But however, what may happen is if you have a signal, see, as we said, if there is low frequencies, okay, the the signal content will not vary much. So here it is not necessary to have a very small window. This can be analyzed with larger window. Okay, window of large duration. Okay, large tau naught is good to analyze. That means even to capture what is the frequency here, we need to complete at least one cycle. To capture that, we need larger duration window. Okay, whereas here if you see, okay, from here to here, okay, tau naught is smaller to analyze the frequency content. If you see from here to here, okay, or here, okay, the window duration that you need to analyze the signal like in frequency content is much smaller. Okay, and hence what the real demand in terms of time frequency analysis is at different durations of the signal, you may need to have different durations of the windows for analyzing the frequency content. Okay, and that is not possible easily in short time Fourier transform because we have fixed the W in short time Fourier transform. Okay, so this is not very flexible. This is the in short time Fourier transform, and this is the limitation of short time Fourier transform. So using signal, okay, with fixed window is not optimal for capturing various frequencies of signals. Okay, and hence we need better time frequency analysis method. Okay, so with varying window, with analysis of signal at multiple resolutions. What do we mean by multiple resolution? Analyzing the signal up to here will give different frequency content. Analyzing up to here will give different frequency content. Okay, and up to here it will give different frequency content and so on. You should be able to look at the frequency content not just from a fixed duration window, but from varying duration windows. Okay, even here if we consider, if we take this window, what we get the content of frequencies will be different. If we get this will be different because the relative variations in time will be different. Okay, with multi-resolution windows, sizes adaptively. Okay, this can be conveniently done through wavelet transform. Okay, this we will discuss in the next class, and with that we conclude our course. Thank you.